Hello everyone. In today's lecture, we can discuss about the base conversions in digital electronics. In the previous session, we have discussed about the different number systems. Decimal number, commonly decimal number system, binary, octal and hexadecimal number systems are used. And decimal and binary is the most frequently required one in the case of digital electronics. So we need to know because naturally the numbers what we get is digital numbers or what we use in our day-to-day life. Whatever we observe, whatever we read, whatever we sense are digital in nature. But when we want to use a digital system to process, we need to convert it to binary system. So we should know how to convert the decimal to binary and vice versa. Similarly, we learn how to convert all these from decimal to binary, decimal to octal, decimal to hexa, similarly binary to decimal, binary to octal, binary to hexa, as well as octal to decimal, octal to binary, and all these conversions, how to make these conversions. So it will be very easy and interesting. First, let us consider a decimal to binary conversion. Let me take this decimal number. So 25 is the decimal number, right? 2 is a decimal number because that number lies between 0 and 9. And 5 is again a decimal number. 25 on a whole is a decimal number. How to convert it to binary? So for binary, the base is 2. So see, I have to divide this 25 with the base number 2. Okay, so when I divide it, I'll get a quotient and this is the remainder. So when I divide 25 by 2, 12 will be the quotient and 1 will be the remainder. Similarly, when we divide, so we have to keep on dividing till we end at this division. And once after completion of this division, we have to write the values from bottom to top. So from bottom to top, that is the reminders from bottom to top. 11001. So this forms the 11001 forms the binary equivalent for the 25 decimal value 25. And suppose if I have a floating point decimal number, how will we convert? So what we need to do is we have to consider this integer 10 and we have to divide this 10 as we did it in the previous case. And we'll get the reminders. The reminders has to be written from bottom to top. Now consider this fractional part, 0.25 separately. So 0.25 has to be multiplied with 2. Why we are dividing it with 2 and multiplying it with 2? Because I have to convert my decimal to binary. I need the output in binary form. So for binary, the base is 2. That is why we are multiplying it with 2 or dividing it with 2. After multiplying, I'll be getting the values like this. And see here, we have to consider only the integer part from top to bottom here. So not from bottom to top, from top to bottom, 0 and 1. So 0 and 1 is the equivalent. So we have to write these two outputs together, right? So for 10, it is 1010. We have written here point. For 0.25, it is 101. So 01. And now binary to decimal conversion. If it is a binary number, how to convert? So see, this is a binary number. 101011 is a binary number. These numbers has some weights. If you see here, this is the least significant bit. That is the bit with lowest weight. And this is the most significant bit, that is with highest weight. So since it is binary number, the weight will be 2 power. Right? So it starts from 2 power 0. So this has a weight 2 power 0. That is 1. This has a weight 2 power 1. That is 2. This has a weight 2 power 2. This is 2 power 3, 2 power 4 and 2 power 5. What we have to do is we have to consider this bit and we have to multiply it with its weight. So 1 into 2 power 0. Then again this 1 into 2 power 1. This 0 into 2 power 2. That is what I have written here. Next 1 into 2 power 3. Next 0 into 2 power 4. Next 1 into 2 power 5. Now when you simplify this, we'll get a value and that becomes the digital equivalent of this corresponding binary value. Now see with decimal part with both fractional and so to the left side of the point we'll be doing it as such the previous one 2 power 0 2 power 1 2. And what about this fractional part? For this we'll be considering 2 power minus 1 2 power minus 2 and so on. So here is an example for that, right? Now how to convert a decimal number to octal? So when we want to convert a decimal number to binary, we'll be dividing it by 2. If you want to octal is 8. So if you want to convert it to octal, we have to divide it by 8. If you want to convert it to hexadecimal, we have to divide it by 16. So decimal to any form of conversions is very simple. We have to divide it by that particular radix or base. Suppose if you have a fractional one, we have to multiply it with that particular radix or base. And the reminders we have to write from bottom to top, which forms the hexadecimal value. Don't forget that hexadecimal value takes only 8 numbers, that is 0 to 7. So this is this how if you have a fractional decimal number, how to convert the same as we did it with binary. We have to multiply it with 8 instead of 2 because it is octal, and then we'll be taking only these integer parts and we'll be writing it from top to bottom. So this is an example both with the integer and the fractional part. So what we'll be doing will be, so this is converting octal to decimal, right? So when we convert binary to decimal, what did we do? We multiplied this number with its weight. Weight is 2 power 0, 2 power 1, 2 power 2 and so on there. Here it is octal number and so the weight will be 8 power 0, 8 power 1, 8 power 2 and so on, and to the right hand side it will be less because that is fractional part 8 power minus 1, 8 power minus 2 and so on. We'll be simplifying it and altogether we'll get this. Now coming to this decimal to hexadecimal. As I said, decimal to hexadecimal, we have to divide it by 16 and we'll be getting the reminders. And see here, hexadecimal means 16 values. So altogether 0 to 15. If you see here, with the outputs are 11, the remainder is 11, 2 and 13. We can't write this 11 and 13 as such. So we have the hexadecimal equivalent. From 0 to 9, decimal and hexadecimal are same. That is decimal equivalent of 8. Hexadecimal equivalent of decimal 8 is 8. 9 is 9. If the decimal number is 10, then equivalent hexadecimal value will be A. 10, 11, 12, 13, 14, 15, right? A, B, C, D, E, F. So this is the hexadecimal equivalent. So see, for 11, the hexadecimal equivalent is B. For 13, the hexadecimal equivalent is D. So we'll be writing from bottom to top. We'll write the hexadecimal values. So this is the vice versa conversions, hexadecimal to decimal conversion. So we have the hexadecimal value. Here obviously we'll be multiplying it with the weight. Weight here will be multiplied with 16 power, right? And we'll be making the calculations. And here I mentioned this one, that is decimal equivalency for hexadecimal numbers. For 10 decimal, hexa is A. For 11, it is B. Then binary to octal. If I want to convert a binary number to octal number, from the right, you partition the numbers into 3 numbers and then convert this binary to decimal. Normal as like we do 1 into 2 power 0 plus 1 into 2 power 2. Right? Individually, every 3 bits has to be converted separately into a decimal value. Altogether, it forms a octal number. And if you want to convert a binary to hexadecimal, we'll be from the right to left. We'll be splitting it as 4. Suppose if you have a fractional part, we'll be splitting it into 4 from the left hand side. Okay, and then we'll be converting this binary to decimal. And if we have any numbers, because this is hexadecimal conversions, any numbers like this, then we'll be writing the equivalent hexadecimal value, and this forms the hexadecimal value. So suppose if you want to convert decimal to hexadecimal value, we'll be converting the decimal to binary and then the binary to hexadecimal. Similarly with octal. So there we have 2 steps, right? So all the conversions, all the base, that is from 10 to 2, 10 to 8, 10 to 16, and vice versa. Similarly, 8 to 2, and all these things we have discussed in this class. These are the references. Thank you.